Hello, and welcome to part 3 of our lecture on chapter 5. In this part of the lecture, we will be discussing non-equilibrium dynamics. In the previous parts of this lecture, we talked about equilibrium situations when there was no net force. In this part of the lecture, we're going to be dealing with the non-equilibrium situations, which are also called dynamics problems. In this case, a net force does exist. And remember, from Newton's second law, a net force causes acceleration. So that's one of the differences in these problems that we're going to do in this section is that the problem will always be involving an acceleration of the object due to the net force. So the object is not at rest and it's not in uniform motion because of this acceleration. So we're going to be using Newton's second law to solve these problems. Remember that Newton's second law is net force is equal to m times a. We can write this in summation form as a vector addition of all the forces. That is our net force, and that's equal to the mass times the acceleration. This is written out over here where we see all the vector forces that are present in the problem have to all be added together to give us the mass times acceleration. Typically, what we will do, in fact, almost always, is we will be breaking up, if there are any vectors, we're going to be working with the components of those vectors. So we'll be dealing with the horizontal forces and adding those together to get the net force in the horizontal direction, and that will be equal to the acceleration in the x direction. And if there are forces in the y direction, we'll be doing the same for those. So several examples will follow that'll make this more clear. For all the problems and examples that we're going to be doing in this part of the lecture, we're going to basically follow a series of steps here to solve these problems. So the first thing is almost always to identify all the forces acting on the object and draw a free body diagram. We'll then use the component equations of Newton's second law and solve for whatever the problem is asking for. So we're going to be setting up Newton's second law, F equals ma, for the x direction or the y direction or both, depending on what is in the problem. And then finally, once we figure out, for example, what the acceleration is, we can use kinematics equations that we learned in the previous chapters to determine things like velocities, positions, and so forth. So let's get started with some examples. So we'll start with a pretty basic dynamics example here. We've got a crane here, and it's lifting a 1,000 kilogram crate. If the cable tension is 10,000 newtons, how fast does the crate accelerate upward? So here's our picture of the situation. Our crane here has got this 1,000 kilogram crate hanging from a cable here. And so let's start by replacing this diagram here with a free body diagram. So here is the free body diagram for the crate. We have two forces acting on the crate. We have the tension force of the cable pulling the crate upward, and we have weight of the crate from gravity pulling it downward. So this is our free body diagram. These are the only two forces present on the crate. Obviously, the crate is off the ground, so there's no normal force. We're going to ignore wind resistance or drag. This would certainly be the case for something slow moving like a crate. So now we can set up Newton's second law. Now, since we only have forces in the y direction, we're just going to add the forces in the y direction and set that equal to ma. All right, so this is Newton's law, net force equals mass times acceleration. So to add the forces together, we just look at the free body diagram and we see that tension points up and weight points down. So we have to subtract those two forces because they're working in opposite directions. We don't add them because they're not working in the same direction. So we have tension minus weight is equal to ma. The weight force, remember, is always equal to mass times g, mg. So our equation now looks like T minus mg equals ma. And we can solve, we're asked to solve for the acceleration of the crate. So we're solving this equation for a here. A sub y means acceleration in the y direction. So all we have to do is divide by the mass here to get rid of that. So we have our acceleration, is equal to tension minus mg all over the mass of the crate. So at this point, we can fill in our numbers. The tension is 10,000, the mass is 1,000, g is 9.8, and down here is the mass again at 1,000. And tapping this out on our calculator, we'll come up with a final acceleration of the crate, 0.2 meters per second squared. Now, one thing we can do here is sort of analyze this answer a little bit. Notice that the acceleration came out to be positive. Can you think about what that means in terms of the direction of the acceleration? Well, since we called the upward direction here positive, remember tension was our positive force and weight pointing down was our negative force. So the acceleration here is a positive number, so that is an upward acceleration. So the crate is accelerating upward. Now, why is that? Well, think of this very basically. We've got a crate here that is involved in a tug-of-war competition. There are two teams. There's tension pulling it upward, and there's weight pulling it downward. Now, which team wins the fight? Well, the tension does. The tension, which you can see here, is 10,000 newtons, remember that was given, is greater than the weight. All right, the weight is 9,800 newtons. It's a little bit less. It's 200 newtons less than the tension. So since the tension force is stronger than the weight force, the crate will accelerate in the upward direction. Let's now do another example. This one has more forces involved. So the situation is 3 men have been hired to move a 400 kilogram wood crate across a warehouse with a wood floor. Joe pushes the crate while Bob and Tim pull with ropes to help. Joe can push with 400 newtons of force. Bob and Tim pull with 300 newtons each. And the question is, how long does it take them to move the crate 10 meters? All right, so let's draw a little picture here of what's going on. So here's our heavy crate sitting on the warehouse floor. This is Joe over here, J for Joe. He's pushing the crate, all right, to the right. And then Bob and Tim are over here. That's B and T. They are pulling on the crate with ropes. So we can go ahead and draw a free body diagram for the crate. It has weight going down, normal force going up, and notice Joe, Bob, and Tim are all creating a force to the right. All right, even though Joe is pushing and Bob and Tim are pulling, they're all pointing to the right. So I'm going to put all 3 of their forces over on this side just to make the diagram look a little cleaner. So I have J, that's Joe, his force is 400 newtons. Bob is 300, and Tim is also 300. That was all given. Obviously, there's going to be friction as this thing drags on the floor. So since they're dragging the crate to the right, we know that the friction force is going to point back to the left. Okay. Now notice, the question here is how long does it take them to move the crate? Well, we can't figure that out until we know how the crate is going to move. We have to figure out the acceleration of the crate first before we can apply any of those kinematics equations to solve for time. So let's go ahead and do this on the next slide. So here's our free body diagram again. Let's go ahead now and write Newton's second law in the vertical or y direction over here. And then over here, we're going to look at the horizontal forces. So we'll do the vertical forces first. This is pretty simple. We've basically got 2 forces acting in the vertical direction. We have weight down and we have normal force up. Now, the simple way to do this without having to write all this stuff out here is just to realize that this crate is sitting on a level horizontal floor and the crate is not moving in the vertical direction. It's only going to be sliding horizontally. So in other words, there's no motion in the vertical direction. So these 2 forces, the weight and the normal force, must be equal, right? There it is in equilibrium in the vertical direction. So we can just set the normal force equal to the weight, okay? Or, more formally, we add up the forces and set it to 0. But it's much faster just to say normal force is equal to weight, and that, of course, is mg, which is 400 kilograms times 9.8 meters per second squared. That turns out to be a normal force of 3,920 newtons. So we'll kind of keep that answer right here. We're going to be using that in a little bit. Now let's turn to the horizontal forces on the crate, acting along in the x direction. So again, we use our free body diagram to guide us. We see we have four forces pointing horizontal. We have Joe, Bob, and Tim forces, all going to the right. So let's call those, let's define that as our positive direction. So we're going to add all these forces together. We're going to add Joe plus Bob plus Tim, and then we have to subtract the friction force over here because it's pointing in the opposite direction. So we're going to say minus F sub K, just to remind us this is kinetic friction. The crate is sliding across the floor. So this is the net force. J plus B plus T minus friction is equal to ma, right? This is Newton's second law. We know that the kinetic friction from the last part of this chapter is equal to mu sub k, that's the coefficient of friction, times the normal force. So let's go, we can make that change here. And now we can throw in some numbers. Joe is 400 newtons, Bob's pull is 300 newtons, Tim, 300 newtons. I looked up the coefficient of friction for a wood crate on a wood floor for kinetic friction from the table that we learned about in the last part of this video. And the coefficient is 0.2. The normal force, N, well, we figured that out over here. It's 3,920, so we'll put that in. So if you add up all these terms here, all right, remember this one is minus, we end up with 216 newtons on the left side. Okay, so that's the net force on the crate. Over on the right side, we have the mass, which is 400 kilograms, times the acceleration, which we don't know. But now we can solve for A. A is just equal to this number, 216, divided by this number, 400, which turns out to be 0.54 meters per second squared. Now that we have the acceleration of the crate, we can apply the kinematics equations needed to figure out the time it takes to move this crate 10 meters. So I'm going to use the position formula here, which says that the distance that something moves when it starts from rest is equal to 1/2 a times the time squared. All right, remember the initial velocity here is 0. So we're going to solve this for time squared by multiplying both sides by 2 to get rid of the 1/2 and dividing by a. So we have time squared is 2 times delta x divided by a. Now the next step is to take the square root to get rid of that square. So the time needed is the square root of 2 times the distance it moves divided by the acceleration. And we know the distance is, remember from the problem, it said how long does it take for it to move 10 meters? So we'll put 10 in there. And the acceleration, of course, we just figured out is 0.54. So we can, again, tap this out on our calculator. Remember, we have to take the square root of the answer there, and it'll turn out to be 6.1 seconds. So there is our final answer. You've probably heard the expression, well, it isn't rocket science. Well, this is rocket science. In fact, basic rocket science is a fundamental part of physics. And we can learn quite a bit about how rockets work without getting into all the technical, gory details that we would have to study if we really wanted to be a rocket scientist. But let's talk about the basics of rocket science. So Rocket Science 101. So the way a rocket engine works, or a rocket works basically, is it has a fuel tank and it has some sort of oxygen supply. And it basically pumps the fuel and the oxygen, mixes them together in a combustion chamber, and ignites this fuel. What happens then is the fuel combusts very explosively, and the exhaust is pushed out of the back of the rocket and directed backwards by a nozzle. All right, this is just kind of like on a hose. It shoots, the water out straight in a straight line out of the hose. That's kind of what the nozzle does to the exhaust. So what the rocket is actually doing here is pushing the exhaust backwards with a lot of force. All right, it's explosively expelling the exhaust particles, the smoke and the particles out of the back of the rocket. But remember Newton's third law, for every action, there is an equal and opposite reaction. So if the rocket is pushing the exhaust backwards, The exhaust is therefore pushing the rocket forward. So here's sort of a schematic showing this. We've got the rocket here. The action is the exhaust, being pushed out backwards. The reaction is the rocket being pushed forward. So that's basically how the thrust or propulsion of a basic rocket works. So using what we just learned about rockets, let's just do a real basic problem here, or at least set up the problem for a rocket during liftoff from a launch pad. So suppose we're given the thrust of the rocket engine, all right? We're given the amount of thrust in newtons of how powerful the engine is, and we're also told the mass of the rocket. First question is, how fast is the rocket going after 30 seconds? And how high has it reached after 30 seconds? So in order to figure out these questions, we need to know the acceleration of this rocket. And so here, of course, is where Newton's second law comes to the rescue. So here's our picture of our rocket. So now we have it taking off vertically, right? It's launched off the launch pad and it's rising up through the air. We're going to ignore drag or wind resistance just to keep this problem as simple as possible. So here's our free body diagram of the rocket. It's actually very simple. We have the weight of the rocket trying to pull it down, and we have the thrust of the rocket's engines pushing the rocket upward. So these are the only two forces involved with a rocket during liftoff. Again, we're ignoring wind resistance. So this is a very basic problem, similar to the couple of the problems that we just did a few slides ago. So in order to figure out the acceleration, we would just have to write Newton's second law. Net force equals ma, and the net force, of course, is this thrust pointing up minus the weight down, and that's equal to ma. And then we can replace, remember, the weight of the rocket, W, is equal to mg, and we know the mass of the rocket. We were given that. We're not actually putting any numbers in this problem. I'm just kind of showing you how we can step through the solution of this problem. So now it's a simple matter to solve this equation here for the acceleration A. We did something just like this in the last question. The acceleration is equal to the thrust minus mg divided by m. I'm just dividing this equation here by m. So now we can fill in these numbers. Remember the rocket's thrust, we're assuming that was given to us, and the rocket's mass, m, which shows up here and here, was also given to us, and g, of course, is 9.8. So we can very easily calculate the acceleration of this rocket. And presumably, the rocket engineers who designed this rocket made sure that this thrust force from the engine is greater than the weight. Because think about what would happen if it wasn't. If the thrust was less than the weight, this rocket could never take off. It would just sit there on the launch pad and burn a bunch of fuel. All right, so a well-designed rocket will have a greater thrust than the weight force. Okay, that's a very basic requirement for getting a rocket to take off. We were asked how fast is the rocket going after 30 seconds. So the final speed of the rocket, remember some of our kinematics equations, is final speed, or velocity, is just equal to the initial velocity, which is 0, by the way, plus acceleration times time. So we would just take our acceleration from the previous step here and multiply it by 30 seconds. And that would give us our final speed at 30 seconds. How high is it reached after 30 seconds? Well, remember also, for an object that starts from rest, the distance it travels is equal to 1/2 at squared. We've used this distance formula many times so far in this course. So again, we would just have to plug in the acceleration from step 2 and plug in 30 seconds here and square it and multiply it by 1/2, and that would give us the height of the rocket at the end of the 30 seconds. We now turn to the dynamics of falling bodies. We talked about falling bodies earlier in the course, in one of the first chapters of this course, and what we learned there from doing experiments and repeating some of Galileo's work is that we found that all falling objects, assuming there's no wind resistance, all falling objects fall at the same speed and acceleration, and they hit the ground at the same time. But the question now is why? Why does this happen? Before we just sort of took it as a fact that could be demonstrated by experiment, but we want to learn a little bit more and see why is this true. This was a sort of a puzzle for a long time. In fact, the ancients, for example, Aristotle 2,000 years ago, claimed that heavier objects must fall faster than lighter objects because they have a greater downward force on them. This is, pretty obvious. If you pick up a small pebble in one hand and a heavy rock in the other, you can tell that the rock has more weight to it, pulling it down to the earth. So Aristotle, incorrectly of course, thought that a heavy object must fall faster than a light object, just because of that greater force. Excuse me. Now, let's take two examples here. We have a 0.1 kilogram weight or mass here, and we have a 1 kilogram mass over here. So there's the difference here in mass is 10 times, okay? So what is the weight force on this lighter mass? Well, weight is mg, so we have 0.1 kilograms times 9.8 is 0.98 newtons. So this is about 1 newton, okay? So this light mass here has a downward force of 1 newton. If we look at the heavier mass now, its weight is mg, which is 1 kilogram times 9.8. That's 9.8 newtons, or almost 10 newtons. So again, we see that this one has 10 times more weight than this one, so it has 10 times more downward force. So why do they fall at the same rate? Why doesn't this one fall 10 times faster? Think about that for a second and see if you can come up with a reason. Now, Galileo lived before Newton, and so he didn't have Newton's laws of motion to help figure out this question about why do things fall at the same. However, Galileo, he was a genius, and he was able to discredit Aristotle's claim just using logic. And in fact, he used a method of argument called Reductio ad Absurdum, which is Latin for reduce to absurdity to disprove Aristotle's claim. This method basically what it involves is you assume that the other person's idea is correct, and you show that it will lead to an absurd result. So this is exactly what Galileo did here, and it's a very clever argument. So Galileo said, okay, let's assume that Aristotle is right and that a heavy object falls fast and a light object falls slow. So in this picture over here on the left, here is our heavy 1 kilogram object. We're going to assume that it falls very fast, and then the lighter object here falls more slowly, okay? So what Galileo said is, all right, let's connect these two objects together. So somehow connect them like this. You can think of attaching them maybe with glue, or maybe just hooking them together with a real light string. But the idea is this: the heavy object, remember, it wants to fall fast. So it's going to try to speed up this light object, which is attached to it. Meanwhile, the light object, which wants to travel down more slowly, is going to try to slow down this heavier object. So if Aristotle is right, then this situation here where they're connected should fall down somewhat at an intermediate speed, somewhere in between fast and slow, because of the two velocities sort of averaging out each other. However, this is not consistent, because think about this. If Aristotle was right, we have just now made a heavier object by sticking these two objects together. So this heavy object should fall faster even than this 1 kilogram object. So you can see that this is a contradiction. It is not self-consistent. You can't have it both falling at a medium speed and falling at an even faster speed at the same time. This just doesn't work. As clever as Galileo's argument was, it really took Isaac Newton's laws of motion to come up with the real explanation of why a heavy object and a light object fall at the same rate. So let's go ahead and look at the way Isaac Newton would explain the situation. So here is our heavy object. Remember, it has a mass of 1 kilogram. So we know, here's a free body diagram. In fact, we're going to ignore wind resistance here. So this has a downward force of weight, which is equal to mg. Now, we can use Newton's second law, net force equals ma, and we can solve for the acceleration of this object. The acceleration is equal to the net force divided by the mass. And by looking at this free body diagram here, there's only one force acting on this falling object. Again, we're ignoring wind resistance, of course, and that force is the weight. So net force up here is just weight, W. But weight, remember, is mg. So we can cancel out the m on the top with the m on the bottom, and look what we get. We get the acceleration of the object is just equal to g, and we of course know that g is 9.8 meters per second squared. Okay, so this correctly predicts that this mass will fall at 9.8 meters per second squared, accelerating as it falls. Let's do the same thing for the lighter object and see what we get. Well, again, here's our free body diagram. It has a downward force equal to its weight, which is mg. And here, of course, m is much less. It's 10 times smaller. So the equations proceed exactly as they do over here. Net force equals ma, a equals net force over m. The net force, again, is just the weight, w. And we replace w with mg. And here it is again. The m's cancel, leaving the acceleration is equal to g, which is 9.8. So what we have just shown here is that in both cases, the acceleration ends up being the same. It ends up being g, which is 9.8. So what about the mass? What happened to it? Well, the key thing is right here. The mass cancels in both cases. The masses cancel out. Now, is that just a mathematical coincidence, or what is the physical explanation for these masses cancel? This is the key to explaining why objects fall together. The 1 kilogram mass has a 10 times larger force of gravity pulling it down. All right, so heavier objects have more downward force, but the 1 kilogram object also has 10 times more mass, meaning 10 times more inertia, so it's 10 times harder to accelerate. So the effects of larger force and larger inertia cancel each other. All right? Another way of saying this is that the gravitational mass is the same as the inertial mass, and those two effects cancel each other out. So as a result, all objects, for example, a pebble, a tiny pebble, and a massive car will fall precisely together. So we have seen earlier in the course, I showed you some video demonstrations of dropping various objects with and without wind resistance. It's worthwhile to revisit those videos just to see the effects again as a demonstration. So we'll watch those now. Our first test is a tennis ball and a 5-pound weight. Our next test is a tennis ball and a 20-pound weight. This test is a 20-pound weight and a light wood block. Hello again. When we do these experiments, we have to be careful about air resistance, also called drag. So let's try doing an experiment here in the garage where there's no wind, and let's drop a heavy book and a coffee filter. What do you predict will happen in this experiment? Here we go.
All right, I'm guessing you were right. And the coffee filter, of course, fell very slowly because of wind resistance pushing on it. Can you think of any ways we can reduce the wind resistance? Well, there's a couple things we can do. The first one is we can reduce the surface area of the coffee filter because that's where the air is pushing on it, creating that wind resistance. So if we crumple it up into a tiny little ball, now we have the same weight, but much less area. So we've reduced the wind resistance. So let's redo our experiment now and see what happens. It's going to be a little hard to see the coffee filter now. But as you can see, they both fell at the same time. Now there's one more way that we can reduce the wind resistance. We can place the coffee filter on top of the book like this. And what that'll do is the book will actually block the wind that's striking the coffee filter to reduce the wind resistance. Let's see what happens here. You can see that the coffee filter dropped just like a lead weight. Thank you.
So according to Isaac Newton, all objects fall together with the same acceleration of g equals 9.8 meters per second. How about if we did this with a hammer and a feather? Well, this is kind of like the demonstration I just showed you with the coffee filter. Because of wind resistance or drag, the feather, of course, on Earth is going to float to the floor very slowly compared to the hammer. We did a couple things in the demo in my garage. I showed you we can eliminate wind resistance by reducing the area. So for example, I crumpled up the coffee filter into a tiny ball and then it fell very fast. Another trick I used was to place the feather or the coffee filter on top of a heavier book to block the wind hitting it, and then we saw that it fell just like the hammer or a heavy weight. There is a third way to do this, and this is the ultimate way to test this, and that is to go to a place where there's no air, where there's no atmosphere. And so the Apollo 15 astronauts did this experiment with a hammer and a feather on the surface of the moon. And remember, this video was taken in the early 1970s, so I apologize for the lack of high definition quality in the video, but it's a very cool video to watch, and so you'll be seeing that next. And while you're watching the short video, keep in mind two things. First of all, watch as the hammer and the feather, watch as they fall together because there's no wind resistance. And the other thing, watch how slowly they fall to the ground. And the reason for this is not because the video is being played in slow motion, it's because of the reduced gravity on the moon. Gravity is only about 1/6 of what it is here on Earth, so the objects take much longer to fall down. So enjoy the video, and that is it for this part of the lecture, and we'll meet again in part 4 shortly.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Superb.